plot the state of the air at the inlets and outlets of the heat exchanger on a Carrier diagram. So Carrier diagram is one of the main psychrometric charts, thermodynamic diagrams that is describing the state of a moist air at a given total pressure. So here we consider that we have atmospheric pressure everywhere inside the system. There are probably fans, but we neglect the variation of pressure due to the fans and to the pressure drops in the lines. And we consider that the pressure is always the same, and we have one given total pressure for one Carrier diagram. The x-axis is the temperature, the y-axis is the moisture content in kilogram of water per kilogram of dry air, and first thing you see on this diagram is the saturation line, which corresponds to a relative humidity of 100%. So, in our case, we know we have 50% of relative humidity for point A and for point C. So here we can look for this ISO curve of relative humidity of 50%. We know also the temperature of point C, which is -8 degrees outside, and so the cross-section with relative humidity 50% gives point C. And we know we have 19 degrees inside the workshop, so the cross-section with the relative humidity curve gives point A. So on this diagram we can also read on this part of the diagram the specific enthalpy, which is expressed here in kilojoule per kilogram of dry air. And so we can read the specific enthalpy of point A, and we can read the specific enthalpy of point C. Let's first look at what is going on for the fresh air that is heated up in this heat exchanger. We know that the specific enthalpy of this air will increase from C to D from a difference of specific enthalpy corresponding to 19.6 kilojoule per kilogram of dry air. So we can just read on this scale, and we can find here the specific enthalpy that will correspond to point D. So we know that point D will be somewhere on the ISO enthalpy line. Then we need to know something else about this point D. And then we can think about the moisture content. When the air is heated up inside the pipes, it receives heat, but there's no mass exchange. So the mass of dry air is not changing, the mass of water is not changing, so the moisture content X needs to be remain constant. X is the horizontal line here, and so X of point C is equal to X of point D, the moisture content of point D, and the intersection between this ISO enthalpy line from point D and the ISO moisture content from point C gives point D at this state. And if we read here, we probably find more or less the same temperature than the intermediate temperature that was calculated previously in part B concerning point D. So, easy peasy for the cold fluid. Now it's a bit more complex about what's happening for the hot fluid. So the hot fluid is at the inlet in state A, and we can also read the specific enthalpy of this state A. But so we know that the specific enthalpy will be decreased by this value of 19.6 kilojoule per kilogram of dry air, and we can also find what's is the specific enthalpy of point B. So we know the specific enthalpy of point B will be, so we know that point B will be somewhere on this iso enthalpy line corresponding to the enthalpy of point B. Similarly as before, if we just have heat transfer without any mass transfer, the moisture content is supposed to remain constant. So if we plot here the moisture content corresponding to point A, XA, we see that it crosses the saturation line before crossing the iso enthalpy line corresponding to point B. And it's not possible at equilibrium to have a moist air which is oversaturated, so something else happens here. In fact, if we cool down one air until it is completely saturated, so this corresponds to what is called the dew temperature, then it's not possible to keep cooling it with a constant moisture content. So if it cools more than this, then part of the moisture, which is vapor in the moist air, will be condensed and transformed into droplets. So here we will have condensation around the walls of the pipes in the heat exchanger. And because the moisture content is only taking into account the mass of water steam, so of water in vapor form, this part of the water will not be taken into account anymore. The liquid part of water will not play a role in the moisture content because it will not be part of the moist air anymore. It will be another phase. So after that, if we continue cooling this air, it will be cooled at saturation, and at the same time some of the water steam will be condensed, and point D will be at saturation, but at the cross section with the a specific enthalpy of point D that we know. And we can read on this diagram that the moisture content of point D is lower than the moisture content of point A.